am Jordan Brandt. I'm with Autodesk. I don't know how many of you guys may know Autodesk or use Autodesk. We've been in the 3D printing space for quite a while. I promise I did not make up the title Technology Futurist. That was given to me. And I guess we'll find out what futurists talk about. And I wanted to start with design and ask a question to the audience. How many of you guys are designers or engineers or anyone in that space? Maybe half the audience, quite a few of you. And so you guys are probably pretty familiar with the process of sketching. And I actually went to school as an architect. Thank God I never became an architect, but it was a good education. And I usually start my designs still with sketching. I use digital sketching now, but that's the method I'll use to explore an idea of something that I want to make. Whether it's going to be 3D printed or manufactured traditionally, the beauty of sketching is it's a very rapid iteration, right? You can get your idea out from your head onto the page or to the screen quite quickly, and you can go through those ideas, right? Because typically when you start designing something, you don't have the full concept of what it's going to be. It's a discovery process. And sketching is very conducive to that process. Whether you're designing characters for animations or for video games, whether you're designing parts for aircraft, like John's team might be doing, designing a car, whatever it is, this is often the process that we start with. And so this idea of iteration is really coming to fruition now. And a lot of the technologies that you see out there are enabling this to happen more quickly, right? So this is a project that we worked on. It's built in WebGL. It's kind of a test that we put together of, can we enable something quickly with a light footprint to allow people to design their own stuff to be 3D printed. All right, it's called Shapeshifter. So you can start with the template, and you can modify the template, modify the size, the properties, so you have a set of sliders. So it's not sketching, but for people who aren't designers or aren't engineers, this is a way for them to come in and actually design and create their own stuff, which is pretty cool. And you can iterate through them very, very quickly. So this idea and concept of iteration is central, and it's central in a lot of themes, right? You see a quote like this, and you may think it's Le Corbusier, or it's Bert Rutan, or it's Yves Bahar. This is actually coming from corporate strategy, right? This book that Eric Schmidt and Jonathan Rosenberg put out about Google and some of the keys to success of Google. And it was about iteration, right? I work in San Francisco, and the motto in Silicon Valley, fail quickly, fail fast, right? Learn from your mistakes. That's all about that iterative process too. So we're going to explore this a little bit more and what that means in a computational sense, and what it means for manufacturing, and what we can do more of. So does anyone in here remember when this was all called rapid prototyping? Todd, I know you should be raising your hand. So yeah, these conferences have been going on for a long time. How long has TCT been going on? 19 years? Yeah, so that was rapid prototyping back in the day, right? And it enables us to go from sketch and idea and 3D model to product quite quickly. The thing is, with most of the systems we're talking about, like the systems that John was talking about, aircraft, cars, buildings, this is the world that I come from, big complex buildings, it's not just a single system you're designing. You're not doing it in isolation, right? You're not sitting there just sketching by yourself. You're sketching with tens or hundreds or thousands of other people. So how do you do that? This image that you see here are just the subsystems in a hospital, right? This is just the ductwork, the electrical, and the conduit, the information systems, the plumbing. This isn't even the architecture, right? This isn't even the structure. And you've got to figure out how to make all this stuff fit inside of a tight space. So how do you do that? Well, this is part of my background. Before coming in Autodesk, I was working in a startup that was acquired, hence the reason I'm here now. And we were developing cloud collaboration technologies, right? How do you invite hundreds of people into your project to help you design and converge on a solution to help you do those iterations? And we found out some interesting things, actually. One of our clients, who was developing theme parks, right? Big complex rides with mechanics and electronics, a lot of moving parts. They were using their design process that they had in-house, which was all desktop-based, right? So they're working on their machine, and they'd email somebody the other stuff, and then they'd invite somebody to the FTP to upload a file, and that typical process that you're probably familiar with. And then when we deployed this cloud solution to collaborate in real time in 3D, they started tracking some information. What you're seeing here, the bottom line, is the process they use pre-cloud, using desktop tools and modeling and iterating that way. And the orange line is post-cloud, and each column represents a week of the design cycle. And what you can see is that they increase the number of iterations an order of magnitude. Not just a few more a week, but tens or hundreds more. And it's because you reduce the barrier to entry, the pain points around collaboration. So given the opportunity, people will collaborate. It's just they haven't had the tools to do that effectively. So again, when you look at these complex systems and the multiple objectives that you're trying to optimize for, okay, this is a PCP chart, not the hallucinogen PCP, although if you stare at it long enough, you kind of get a similar vibe from it. So this is used to map multiple objectives and to figure out which solutions are best fitting all those multiple objectives. So basically what you have, if you haven't seen these before, imagine each of these vertical planes as one of the criteria that you're targeting. So it could be a constraint on the system, or it could be a parameter to optimize. And each of the colors, each of these threads are one solution. So it's showing you each solution and its performance to each of those criteria. And you can imagine that if you're optimizing for, let's say, structure or stiffness, if you achieve that structure or stiffness by adding material, then you're going to de-optimize your weight, right? So a lot of these are trade-offs. And it's a very complex problem. I mean, there's hypotheses that a very, very exceptional human can hold maybe 6 or 7 parameters in their mind simultaneously. And now we're getting into systems that have dozens or hundreds of criteria that we're trying to optimize for. So how do we do that, right? And I would argue that we cannot do it explicitly, meaning you cannot explicitly design these things where you take the idea in your head and you draw it out. It's just becoming way too complex to do it in that method now. And instead, we're focusing on what are the criteria we're trying to optimize for and let the system generate potential solutions. And then we can evaluate those based on those criteria. So what you're seeing behind me is a project we're working on with a company called Moon Express. And these guys are badass. They're a startup in San Francisco, just south of San Francisco. And they're sending a lunar lander up next year. It's going to ride on a SpaceX rocket, so another private company sending people to space that just sent the first 3D printer to space, was it last week? That's pretty cool. So these guys are trying to develop this lander, and obviously weight is a huge consideration. So we worked with them on this bracket. So this bracket is basically holding the thruster in place, connecting it to the fuselage. So the big yellow thing, the big tube, is the fuselage. The kind of transparent gray thing is the thruster, which has multiple degrees of freedom. And so just instead of designing a bracket as you or I might sit down and draw, we generated this computationally. And you can look at that and you can assume that it's probably not the first solution that a human would converge on, or even a group of humans would converge on. And in fact, this solution was grown, right? So we're using genetic algorithms to seed different possible solutions, right? We're searching this big, big solution space, and we're growing solutions, and we're analyzing each of those and testing their performance. The thing is, what you're seeing behind me happens 3 times a second. We grow it, we analyze it, and try another one. We've slowed it down for your viewing pleasure. So we can do things that even big teams of humans can't do, at least in generating design options. Now the truth is, though, this algorithm has no idea what a good design is. It's not a designer, right? It's just trying new things. And if you think of this as accelerated evolution, right? Evolution is really just taking 1 billion shots in the dark and hoping that one of them hits, that one of them is a good solution. So how do we make this search more intelligent? How do we target this so it's not searching every possible idea, every dumb idea? I mean, genetic algorithms are really good at finding a dumb idea very quickly. So how do we target this search, right? How do we look at what nature has done, for example? Humans are here, so one of those 1 billion shots in the dark worked for us, at least so far if we don't screw it up. So we're working on a project called Project Cyborg. It's in limited beta now, so you guys can sign up and send a request. And with this, we're modeling and simulating molecular systems. So we took some of our software and multi-physics analysis capabilities and said, what if we could simulate the way that molecules combine themselves, right? What if we could simulate RNA transcription? What if we could simulate the way cells interact? What if we could look at self-assembly? So if you start analyzing systems at this scale, really the only way that we're going to realize this in the physical world is to make them intelligent enough to assemble themselves, right? If we have a device picking and placing things, which there's what, 40 to 70 trillion cells in our body, we're not going to get there very quickly. So we got to think of other ways to make these systems come together, which leads me to talk about machine intelligence, which is obviously embedded in a cat GIF. So I use this to talk about Google image search, and specifically their image recognition capability. Now, all of us, probably for every presentation we've ever done, leverages Google image search heavily. What's cool now is that it doesn't have to rely necessarily on the data that the user tags in it. User doesn't have to put in cat. It can recognize cat. So the question is, how did they get it to do that? Well, the developers and their deep learning team, instead of telling it what a cat looks like, they said, why don't we give you millions of images and let you figure out what cat looks like? A machine learns in a very different way from us. So they're using neural nets or a sequence of stages that it passes through and filters information in a certain way. And what's interesting about this, the outcome is that it's now starting to outperform humans. And they ran a test actually with paper shredders. Very banal, innocuous paper shredders, right? They all look the same. Well, it turns out that their image recognition can identify paper shredders, the brand of paper shredder, the specific vintage, if you will, better than humans can. Now, the scary part of this is the only way they can tell you how it identified that paper shredder is to reverse engineer the code that the machine generated. They didn't write that code directly. They wrote the code to write the code to find the thing, right? Now, this isn't the first industry to have this situation arise. Algorithmic trading has been around for a couple of decades, and we have these events like flash crashes, where suddenly the market tanks really quickly, faster than a human could think. How did that happen, right? Most of the volume is done by algorithmic trading. And what's happening is that the people who wrote the original algorithms that modify themselves based upon performance over time could not tell you necessarily why an algorithm made a specific trade. Meaning the original plumbers, as the author writes here, kind of lost control of the system. Now there's checks in place, so don't freak out. The world's not going to end tomorrow. But the point being, we're starting to create systems that can modify and evolve themselves over time. And that's what's going to take all the stuff out here to the next generation, to the next level. It's not going to be by us drawing it. It's not even through topological optimization. That's a step in the right direction, but it's not going to get us all the way there. So we have a new product that we released called Fusion 360, and it's 3D modeling in the cloud. And what's cool, it's also the simulation and the manufacturing. So you're going to have it all in one place. So it's got direct modeling where you can shape surfaces and make cool designs, but it also has all the mechanical design, so you can do your gears, your more complex mechanics. And then you can take it all the way to CAM or to 3D print. Now, I bring it up not because of the capabilities of the software, but because it is cloud-based, gives it a certain edge in the sense that now there's a lot of designs. There's a community around it. There's a place where you can start to find intelligence that emerges. Right? So think about how many times your companies, how many times has BAE designed a bracket? Thousands? Hundreds of thousands? So what have we learned over the years of bracket? How have we codified that knowledge other than some really smart engineer has it all in their head, right? With cloud-based tools, you can start to do this. You can start to find what solutions have been tried before and how well did they work, and how do we adapt that solution to the new context. So we have a research project underway around design graphs. And the idea here is, first of all, let's be able to search on geometry and nothing else. Similar to an image search and recognizing what's in the image. Let's just recognize what the geometry is and be able to group similar geometries. So no metadata, no user tagged information, just the geometry. And let's figure out where those geometries were applied, in what context. What was the solution what we're going for? And once you get that, then you can start to mine more data. So what you're seeing here is searching specific projects, buildings, vehicles, consumer products for similar geometries and finding the context of a solution. And then we can go to say, well, how well did that solution work in that context? So here it's finding elbow, the geometry elbow, and all the instances of elbow that might exist. In this building, you have HVAC elbows, you have electrical elbows. Humans have elbows, right? What was the context in which they were used? In this case, the elbow was used on an excavator specifically for the exhaust. And then we could also find out, well, how well did it work in that context? Could we reuse this bit of information? So I'd bring this up as the ability to now start searching all the information we've been building up over the years, which right now is not being leveraged very effectively. Now, this isn't intelligence, right? This is just data and statistical probabilities. It's not human intelligence. It's not cleverness or intuition. This is actually now the groupings of that search space. So we search for geometries, and now it's starting to group all the little squiggly marks that look like strings of bacteria, are actually the groupings of those like geometries. So I say a robot is no more a craftsman than an algorithm is a designer. That's very much true. The point here is that we can start to teach the robots, we can teach those machines how to design with us collaboratively, and how to teach the robots to work with us collaboratively. It's not an either or, it's a both and. So we've been exploring this in the office. This is actually a friend, a guy has a desk a few steps down from me. And he's taught his robot how to paint. Dr. Woohoo. And it's really cool because it's on his desk. You can see it here. It's in the office environment. And it's a force feedback machine, so that if it comes and punches you in the face, it might leave a bruise, but it's not going to kill you. And people can walk by and teach it how to paint a painting that they want to do, right? He's programmed it to remember where the paint is and how to mix the water and the color and all of that. You can come by and just grab it, teach it how to paint, and it'll paint it. Now, I lovingly named him the Bob Ross bot. I don't know how well this translates, but in the US, there's a lot of kids who are happy now because their rainy afternoons was spent with Bob Ross. But the point here is, again, how do we collaborate with the machines? There's a lot of interesting things happening in the industry. Toyota made this announcement as probably 4 or 5 months ago, that they're replacing a lot of their machines with humans in the assembly line, in the factory. Like, why the hell would they do that? They're practically invented a lot of these automated processes. Well, they realized that an assembly line or a factory full of just robots is never going to improve itself. One robot's not going to look at the next robot and say, hey, you're doing that wrong, or why don't you try this? So they realized that they took the master craftsmen, the people that they're about to lose, the people who are about to retire, and they put them strategically in certain locations. They could improve production capacity, improve quality, continual pursuit of quality, right? So big industry is starting to look at this too. Now again, this is about the augmentation. So where I see additive and everything out there in the near term is augmenting existing factories. I mean, we know the case studies of printing injection molding tools with conformal cooling. It's getting 20 to 40% production rate improvements in an industry that's been trying to get production rate improvements in orders of magnitude of a fraction of a percent for decades, and suddenly, almost overnight, boom, it's huge. It's augmentation, it's both and. Right? So what's happening now in the world, you've got software, you've got hardware, and you've got materials. And the three are indistinguishable. They're mutually exclusive, mutually inclusive. And it's really hard to innovate in one without doing all three. Right? And some questions start coming up. I mean, you think about the IP. Is the IP in the material that's being placed? Is it in the machine that's placing the material? Or is it in the software that's telling the machine where to place the material? My bet is probably all three. All right, think about standards. We hear about standards a lot. But what happens when every material, not just the product, but the material itself is bespoke for its purpose? The material has never existed before in the history of the universe until you made that one specific product. What does ISO do with that? And then think about the complexity that we're about to enter and the orders of magnitude of data that we'll have to deal with. When you're starting to place every bit of material, even down to the molecule, these files that you've been dealing with, and whenever people come to me, oh, you're with Autodesk, and can you make STL files better? It's like, I don't care about files. Files are dead. Files are not going to be relevant in a not too distant future. So why did Autodesk build a 3D printer? And for those of you who don't know, we are building a 3D printer. The idea isn't that we want to take over the 3D printer hardware market. It's that we want a demonstration platform for an open source 3D printing technology we're building, right? Open standards. So the printer itself is a DLP printer, made solid, did some reviews of it recently. We've shipped out a bunch of beta machines to material suppliers, even third-party machine manufacturers, to let them play with it and test it. We're releasing, once this machine is publicly released, we're going to release all of the blueprints, the material formulations. It's meant to be hacked, right? That's the intent of the machine. And it's meant to prove as a demonstration platform for Spark. And Spark, think of it as, again, an open platform that third-party material suppliers, hardware manufacturers, and software providers can plug into. Basically, we saw so many companies coming in who are solving the same problem over and over. Support generation, G-code generation, slicing, all of this. And most of them were not innovating, they're just replicating. We said, why don't we just do this base level, this base standard, and automate a lot of those features so you, as a new 3D printer startup, can focus on the important stuff. Make your machine more reliable. We don't care about your software. It's not anybody better than anybody else's. And then for the software providers, also let them focus on what they do well and not replicate the same stuff over and over again. So I'm really excited about this. This was an announcement around Local Motors, who 3D printed a car. The car chassis is a bit more apt description. And we're working with Oak Ridge National Labs, who printed this on their BAM, Big Area Additive Manufacturing Machine, made by Cincinnati. There's a lot of things we're targeting, but you can imagine G-code generation for these very large format machines is a different beast altogether. So you'll be seeing a lot more stuff like this coming out. Now, to kind of wrap this up, and looking at the small scale, again, I talked about the exponential complexity of the data we're going to be dealing with. We've been working with Lawrence Livermore National Labs, who has developed, amongst other things, a negative CTE metal, negative coefficient of thermal expansion. So when it heats up, it shrinks, and when we cool it down, it expands. Talk about materials that have never existed in the history of the universe, this is one of them, right? And they're actually compiling this stuff. They're getting about 100 micron feature sizes. And now imagine when every one of these little octet trusses is unique. Right now it's kind of a copy-paste, it's a pattern, but you can imagine now, what if we can tune the CTE of a specific part? You think about optics in outer space, right? As a telescope or any kind of device with optics that have very high precision go around the Earth, they get really hot and they get really cold. What if you could design it to have 0 CTE? Pretty applicable. So the data sizes, if you imagine that we're printing at, let's say, the micron scale, you can do micron scale features, which is already happening in some scenarios. And let's say it's about 50 kilobytes to inform what material goes there for each micron. Something the size of the phones in your pockets be about 3.5 petabytes of data for something that big. How are we going to scale that? How about when every one of these things is unique? It matches your DNA or your thermal profile. So it's going to get huge very, very quickly. So even AMF, whereas I love the new capabilities, it's not going to cut it. Now there's something I think is a precedent. Does anyone recognize this little block? How about now? It's a few younger ones nodding your heads, but parents, come on guys. This is the future, man. Minecraft. Yeah. It was what, a $3 billion future for Mr. Persons? So people are now designing, I mean, get this. In this GIF, you've got people designing printers in Minecraft, functioning printers. People designing functioning CPUs. People designing functioning hard drives. You can actually read and write data in this metaverse, which is a very meta-philosophical kind of thing. But what could happen if you just hit compile? I've already built this thing. I've already built all the material properties into this, all the conductivity, all the insulative values, the structural values, all that stuff is in those little blocks. Now what if I could just compile that? all right? And by the way, talk about collaborative, you can actually see the other people. When I play with my nephews and nieces, there's like 10 of us running around. One of us is deleting the stuff that the other one just did, and the other one's like chasing them around with a stick. It is collaborative, right? It's fun, too. So why are we talking about all this? And we're talking about the education of the engineers. John was talking about this at BAE. We have similar discussions with our clients. How do you unlearn all of this rigorous training that you've had to embrace what additive can do, what computational design can do? I think there's people already doing it. All right, so the final word is let your kids play. If you think they're wasting their time, they're not. They're compiling the new universe. Thank you very much.